do them in an hour and a half.
Kevin?
Yeah.
Are you going to do a break for the session?
What?
Are we getting a break?
Yeah, I'll do a break right after. I'm going to finish the lecture as
Yeah,
well,
sure.
and then we'll take break, then practice exams.
Yeah.
Okay, so logistic regression, the motivation here was in order to do naive Bayes, what we really did is we computed the joint and then got the conditional out of it by doing Bayes rule. Why don't we just compute it directly? We can do that with logistic regression. So, but we have to make different assumptions. So, what we did to motivate logistic regression is we took the conditional independent assumption of naive Bayes, carried the map forward, and arrived at logistic regression, even though logistic regression doesn't really make strict conditional independence assumptions. But it doesn't matter. Anyway, the point here was just that if you run through naive Bayes, you can end up with this logistic form if you move it around. And if you make certain assumptions about Gaussian naive Bayes regarding the distribution here in Gaussian naive Bayes, then I actually have a translation function. This doesn't mean it's a one-to-one mapping. It just means that for a given specification of naive Bayes, I can convert it into logistic regression. It doesn't mean that I can convert the weights of logistic regression like back into.
But if I do naive Bayes, I'll have like a unique set of weights. I don't.
Yeah, so you don't. If conditional independence is true.
Yeah, conditional.
If your assumptions are true and you do naive Bayes, I can take your naive Bayes weights and convert them into a linear function. That logistic regression would have learned also.
Yeah.
So what's here to say? Oh, so this is a linear function. There's my decision rule right here. Nothing particularly compelling. This is a logistic function, very poorly drawn, because it's actually symmetric around this. To generalize to a multinomial, you just have one linear function for every class. So for k less than k, it's that, and then I have the 1 because it has to be a valid distribution. Okay, so in doing logistic regression, we want to get the maximum likelihood, or the maximum conditional likelihood estimate. So we have our data, and the issue is even though this is a convex function, there's no closed form. Where do we get to this? Data likelihood, okay, yeah. So this is my data likelihood, this is my data conditional likelihood. This is my maximum conditional likelihood estimate, is just the arg max for that given likelihood function, as it always has been. We can take the log, and the log, returns. Yeah, we can get a log likelihood, and this is our functional form that we showed before. But the point is that while I want to choose a weight vector that maximizes conditional likelihood of the data, I can't actually do it because even though it's convex, there's no closed form. So gradient descent, or what we do is we just take the derivative with respect to the weights, or the error with respect to the weights. So this is actually, it's on the practice exam, so it's something that's kind of important. This gradient descent is now, you've seen the first lecture again. You could do gradient descent or stochastic gradient descent. You can do this you could learn, you learn EM this way, effectively. You learn linear, LMS is a linear regression. We show in this lecture how to do it for logistic regression. But it ends up basically being the output minus what your prediction is times the value of the x that you're updating. That's what it always works out as. Math is nice, but it's not really super crucial. So gradient descent for logistic regression, this is my log likelihood, expand it out, and if I take the derivative with respect to the weight, I end up that it's y minus the predicted value times the feature value at that coordinate. And this is the questions I had about comparing naive Bayes or Gaussian naive Bayes to logistic regression. More of a discussion that you can't really do anything about, and I don't know why it's scan diagonal. I swear my scanner didn't do that. Maybe I don't. Yeah. Okay, what did I do here? Oh, so how about map? So map is the same deal. It's just that I define a different prior. That you define a prior nonetheless. But this looks a lot like regularization, where you've seen the function I have a few times. We have a minus lambda regularizing, and often what you'll do for linear functions is just squeeze down the weights. And again, that's in the practice problem, so I'm not going to say too much about that. Okay, 1 second. Okay, so this was the regularization, but this is a prior over the weight vectors. It looks like the weight magnitude. So this is kind of a summary. There's two serious ways to do this. One is generative. Assume some functional form for p of x, y, and break it down into a prior and a class conditional. Estimate the parameters and use Bayes' rule to get my conditional back out. The other is discriminative, where I assume some functional form for the conditional directly and estimate the parameters accordingly, such that I minimize some loss. That make sense? Already talked about regularization. Oh, this is my explanation about the paper I talked about. That when does naive Bayes work better and when does just regression. Obviously, I'm not going to ask you something specific about a paper written 10 years ago. Yeah.
Well, like we could expect questions as to like which model works better. With, like,
yeah, I mean, I could say something about linear functions or.
You do ask about like what's better when you have assumed
finite data or.
Yeah, that's true.
Assumed distribution.
Yeah, that actually ends up being a really bad question. I thought about it.
Does that mean that we can still assume conditional independence on that question?
No, no. If you think the point is good, but the issue is if you start playing with what the direction of dominance, it's not. When we get to the determinacy, it's not really 100% clear. What I really should have said was, we'll get to it. Okay. So what you should know, everyone can read this page themselves, but logistic regression, a functional form from the naive Bayes assumptions. It training optimizes parameters without conditional independence, so that's why it sometimes does better because conditional independence usually doesn't hold. MLE, pick a weight to maximize the conditional distribution. Map, pick a W to maximize the probability of that W. Regularization, and gradient descent. And that's about it. Okay. Linear regression. Yeah, still. I know I'm going like way too fast, but I want to get to the prices. Stop me if you have questions, though. Don't be overly shy. So far, we're assuming classification. If we want to do regression, what we'll do is we'll model this in a different way. I'm turning the page. Okay. So we choose some parameterized form, as we did for logistic regression for this conditional distribution, and then derive some learning algorithm based on MLE or map for that functional form. So our parameterized form for our linear regression is effectively this assumption that I have some linear function and then some Gaussian noise. So there's some error function. So essentially it's a mapping from x to y plus some noise function. As I say here, y f of x plus epsilon, where epsilon is normally distributed, zero mean with some variance. because the zero mean means it's right on the line, and the variance just means how much it slides off of it. So this is like pretty much what everyone does. It's not I didn't invent this form. It's probably so well known that the inventor of it probably doesn't get credit for it. It's used too many times. What are we going to say here? Expected value of y is going to be f of x, because the noise is going to be IID and symmetric and all that kind of stuff. So we don't know the error, but we know the form. So that means that our linear regression looks like this, that essentially f of x is the mean and the noise is the variance. Not super, whatever. So in order to train linear regression, as I said, there is a closed form solution that you should figure out at some point in your life, but we only did stochastic gradient descent in this case. So we could do gradient or stochastic gradient descent. So again, the same dance we've done before. This is our maximum likelihood estimate of our weight vector. And we can do gradient descent, so we take the log here and take the derivative with respect to w. And if you work hard enough at it, it looks like this. That is just the output minus the functional form, which it always is for gradient descent. Yeah, so, and if you want to do stochastic gradient descent, you just use this over and over as you see in homework 3. Whatever the problem set, last problem set released. Okay, so summary for regression, in the interest of expediency. This is our assumption for linear regression. MLE corresponds to minimizing the sum of squares of the prediction errors for this particular case. Map estimate minimizes sum of squared errors plus sum of square weights. So that's the case where we're trying to minimize the size of the weight vector, or the magnitude of the weight vector. Learning is optimization procedure, maximize the data likelihood or the posterior, depending if we're doing MLE or map. And we can use gradient descent if the objective function is differentiable with respect to w, and you can live with local optimum depending on your functional form. That's all for notes. Yeah?
So in the linear regression, are we only learning the weights, or are we also learning the sigma?
No, you're only learning the weights.
Okay.
Yeah, because the sigma, I mean, yeah, because we're just trying to find the expected value. The sigma is, we know the form of it, but we don't know the individual values, and we're not trying to predict the values anyway. Okay, let's take a break. Anyone who has questions, spit them out, or we'll start again in